All right, Unit 1 review. So for the first one, we're looking at our limit as x approaches 0. And as always, we always try to plug in first. And if we do get, or when we do plug in, we will get 0 over 0, which means that we are going to have to do some kind of algebra magic, is what we called it. And so we need to do some kind of factoring here if possible. And so it looks like there's a GCF. So I'm going to, again, start with our limit, x approaches 0. And in the numerator, I'm going to divide out 3x squared out of each term. So I have x cubed plus 4. And that's all over, and I'm going to be able to factor out x squared in the denominator. So I have 5x squared plus 6. The x squareds will cancel, and now when I evaluate my limit, in the numerator I have 3 times 4. In the denominator, I'm going to have 6. So this reduces down to 2. So it looks like we're going to have answer choice C. All right, moving on to the next question. This one is a one-sided limit. And again, if we do plug in 0 or plug in 3, we're going to have 4 minus 9 in the numerator over 0. So here I have negative 5 over 0, which is a vertical asymptote. We know something is going on around 3. Now we want to approach from the left, so this is where we chose a value, let's say 2.9, nice value to the left of 3, and we subbed in, and we were not really interested in the final number so much as we were with the actual sign of it. So we have 2.9 minus 3. In the numerator, we're going to have a negative. In the denominator, we're going to have a negative. So that tells me that this is tending positively. So we're going to have answer choice B. All right, number 3 is an intermediate value theorem problem. And we do have to examine the pieces that we have to be sure are present. One, f is continuous. We have this closed interval. And we're given our f at A and f at B values. So we do have to remember here we're looking to see if there's an x value that exists. So here we have, I would go ahead and plot these 2 points. Now it's just a rough sketch of what's going on with them. We have 3, 9, and then we're going to have 5, 22. That was 522, and this point down here was 3, 9. Now, what the intermediate value theorem is going to suggest is over this interval here, and we can dot this off and try to help pinpoint what's going on with this. So, according to the intermediate value theorem, there's got to be a y value. Let's see, we have 22 and we have 9. So somewhere between 9 and 22, there's a y value that goes with this x value that's somewhere between 3 and 5. So if we know that, then we automatically, we know those 2 things are not going to be the answer. Now, notice that A and B are worded very similar, and notice that 11 and 13 both fit between 9 and 29. Now, we all want to say that the answer is B, but actually it's not. The right answer is A, because even though 4 does fit the whole idea that we're between 3 and 5, we don't know that f at 4 maps straight to 13. We don't know that. We just know there's an x value that will give us a value that's between 22 and 9 here. So the right answer for this one is A, and B is just a very good distractor. All right, to this problem, And first thing we're going to do is figure out what does f of x plus h look like. So f at x plus h is going to be 3 times x plus h all squared plus 4 times x plus h. And then we're going to have to FOIL this, and so I'm going to do the foiling in my head and go ahead and get that out of the way. And then I'm going to go ahead and distribute this also. So I'm going to have plus 4x plus 4h. And finally, let's go ahead and distribute our 3 to each part. All right. And notice after we do the substitution, there's nothing that's going to combine, and that's quite okay. It shouldn't be combining right now. Now we're going to look at minus f of x, and then we'll put the two together and do our limit. So we have negative f of x. So that just means I'm going to multiply every part of this function by negative 1. So I have negative 3x squared minus 4x. Now at this point, when you're ready to write in your limit, you should have stuff to cancel. So I have my limit as h approaches 0. Those will cancel, so I have 6xh plus 3h squared, and then notice the minus 4x and positive 4x, and then plus 4h, and that is all over h. We do have that GCF of an h, and most of the time that should happen all over h. And now when we apply our limit, notice we're going to have 6x, that's going to go out to 0, plus 4. So that's going to give us answer choice B. Okay, with these problems, and to me they can be tricky, notice that you're looking for the function, the reason why g of x is not continuous. And notice that they've given us really the 3 steps to show that we are continuous. That is the 3 steps. And so we just need to verify which one's true and which one's false. So for the first one, we need to see that g at 2, it says, is undefined. Well, right here we see g at 2, though. We can't really, I don't think that's really going to be truthful, is it? Because I see that g at 2 is going to be 2 square root of 2. Okay, now let's see, so that can't be why the function is not continuous, so let's cancel that out. That's a false statement. All right, now let's look at the second one, this limit. So we have to look at the limit as x approaches 2 from the left of the function, and we need to compare that as x approaches 2 from the right of the function. So we have to compare those two. Excuse me. So the limit as x approaches 2 from the left, that's going to be all these values that are less than. So that's going to be sine of 2 pi over 3. And I want to know, is that equal to the limit from the right? It's going to be the bottom piece, which is going to be 2 square root of 3 all over 2. So let's see, that's going to give me the sine of 2 pi over 3. That value is the square root of 3 over 2. And that's definitely, on this one, those 2's are going to cancel, and that's not equal to the square root of 3. So I see 2 here, this limit, those from the left and right do not equal each other. So that definitely is a possibility. So we've gotten rid of that, but we still don't know about 3. So let's check and see with 3. The limit as x approaches 2 equals g at 2. Well, g at 2 is 2 root 2, and that's definitely not the limit because the limit doesn't even exist. So that looks like there's another reason why this could not exist. So it looks like we're going to get answer choice D. Okay, for number 6, Notice we're talking about x is approaching infinity. So if x is approaching infinity, then this is where we talked about our power struggle. And we need to find the largest term that we have in the numerator, which is going to be that 8x cubed. And we're going to compare that with the largest power in bottom, which is going to be 3x cubed. And so this is going to be a power struggle here, but notice these two exponents are the same, so this is a balanced power struggle, so they're going to cancel each other out. And when they do, notice that my limit is going to be 8/3, which is C. And by the way, just keep in mind that that implies also that you have a horizontal asymptote at y equals 8/3. Those things all mean the same. All right, so number 7 can be a little bit tricky. Again, x is approaching this time negative infinity. We are going to grab the highest power we see on top, which is a negative 3x. We are allowed just to really omit that positive 3 because it really becomes obsolete as x is growing without bound. Now, if we look at the square root of x squared, this one, it becomes a problem area. That answer is always positive. Always positive. We cannot take the square root of something and get negative. So no matter what big negative x value I sub in, we're always positive in the denominator. So I'm just going to go ahead and put a positive down there. And really, we need to keep in mind that's a positive x always. So, why don't we just put absolute value of x? Because that would mean the same thing as this over here. So we can think about this as a negative big value that we sub in. So I'm going to say negative 3 times negative big. And that's all over the absolute value of negative big. That's one way to think of it. So on top we have 3 positive big over positive big. And so notice this will balance out and be positive 3. So you have to be careful with those. Pay attention to the signs. All right, in number 8, we're going to talk about which of the following statements are true. So I'm looking for true statements. So let's examine one. We need the limit from the left, which is this up here. They're saying that's equal to negative 2. So let's see, what is the limit from the left? We're going to have 4 minus 6. So yeah, that is equal to negative 2. So that one's true. So that means it can't be that or that. So notice very quickly we figured out that we only have to look at answer choice 2. And so it says the limit exists. Well, I know the limit from the left, I just saw that to be negative 2. I need to see, does that equal the limit from the right, which looks like it's going to be 4 minus 5. That is not true. So it looks like my only answer choice is going to be A. And number 9, we're looking to see if we have a true or false statement. Now, this can be misleading. These properties over here, those would be true if you have a polynomial. That's only if you have those polynomials, then you're guaranteed it to be true. These are rational functions, so we're not necessarily guaranteed these properties, and we do need to investigate them. Now, for this first one, notice here and here you have a common denominator. So our limit as x approaches 4, that's really going to be 2x minus 8 over x minus 4. And so here we need to factor out a 2 in the numerator. And so I have the limit as x approaches 4 of 2 times x minus 4 over x minus 4. And so notice that limit value is going to be 2. And so, because that's the only thing left, and if we have a constant, then that's going to be our answer. Now over here, it's almost like we're comparing these two. This one, we need to work out our limits separately. In other words, I'm going to work out this part first, and let's see what that means for us to do. We have the limit as x approaches 4, and notice when I plug in, I'm going to have 8 over 4 minus 4, which is 0. So that automatically is going to be a vertical asymptote. And that means here, since it's not one-sided, this limit does not exist. So automatically we see that number 9, we're not going to get the same thing on both sides. So we're going to get a false statement. And again, if you're not sure and want to look at this other side, well, same idea here. We're going to get 8 over 0. And this is a one-sided limit, so it does not exist. All right, so let's look at number 10. And number 10, again, going through, it looks like it's the same type of problem, but we're looking at them divided up individually. And these are probably not going to be the same, but we need to investigate and see. So if we plug in a 1, we're going to get 0 over 0. So we're going to have to do some factoring here. And in the numerator, it looks like we're going to have x plus 7 times x minus 1. In the denominator, I'm going to have x plus 6 times x minus 1. So it looks like we're going to have a removable discontinuity. I'm removing it. And so when I sub in my limit value at 1, it looks like the numerator is 8 and the denominator is 7. All right, let's compare this over on the other side. So in the numerator here, when I sub in 1, it looks like I'm going to get 0. And then over here on the bottom, if I plug in 1, again, I'm going to get 0. And so this is not going to be defined at all. So here, we would have to go through and do something called L'Hopital's rule, and we don't know how to do that yet. But something for sure that we can say is this side does not exist. That's not going to work for us. All right, in number 11, by the same ideas as what we've been doing, we need to investigate the left side and then come over and investigate the right. If we plug in 1, we're going to have negative 2 over, and the denominator, we're going to have 1 plus 2 minus 4. So it looks like we're going to have negative 2 over negative 1. Now let's compare that over here on the other side. If we find our limit in the numerator, we're going to have negative 2. And in the denominator, it looks like we're going to have the same thing. We're going to have 1 plus 2 minus 4. So notice here we get the same exact value, top and bottom. And so here we are going to say this one is true. And if we looked at this graph of this polynomial down here, even though we've got a rational function, that one's not going to have any real zeros to it or any breaks in it. Continuing on with our true and false statements here, notice this first one, or number 12, we have the limit as x approaches 5 of our function is 2. So notice right here, if we're talking about dividing this up, we need to see, well, is it not going to exist? So let's see if we have the limit as x approaches 5 of f of x, and then is that going to be, let's see, gosh, yeah, I think this one's going to work because you're going to have the limit here over g of x. And notice that when we apply these limit properties, the limit as x approaches 5 of f of x is 2, and g of x is 0. This is just a limit. It's not one-sided, so this limit does not exist. 5 is a vertical asymptote for our function here. So number 12 should be true. Okay, number 13. Let's see. This one's going to be a little bit different, though. It's the same idea here and here. And notice we're going to get 0 over 0, which we don't know what that equals. That meant we had to go back and do some factoring or some kind of rationalizing. So to make the statement that this just does not exist, that's going to be false. We don't have enough information to determine that yet. The same should be with number 14, because just because the limit here exists does not mean that it exists at the actual value of the function. Remember, the limit is the intended y value, so if we have something that looks like this, and notice here we'll call that 6, and we might have a y value here of 5, but the actual function's value could be way up here somewhere or way below the x-axis. So just because the limit exists does not mean these individual values do exist. So that is false. Number 15, you've got a polynomial. Polynomials behave very nicely. They're continuous everywhere. So this is the final statement to our continuity. And so this one's going to be true because it's basically saying that our polynomial is continuous at x equals b, and it should be. Number 16, it sure would be nice if that was true, but it's not. This one is false, no matter how much we think it needs to be true. X is approaching 5, a function, so notice f of x is infinity, and g of x, same idea, approaches infinity. The reason why this is false is infinity is just the idea of a big number. It does not imply that these two are the same amount. Nothing says that they're the same. So you can't say infinity minus infinity is 0 because this number, even though it says infinity, it could be bigger or smaller than this number over here. Because again, we're just talking about the idea of a big value. We have not assigned any specific value to it. Number 17, the line x equals 1 is a vertical asymptote. And so f at 1 is not defined at 1. No, that one again is going to be false. Our graphs don't cover if we have a vertical asymptote. But if you had a piecewise function, let's say that, let me erase that. Let's say f of x equals, and we're going to say it equals, let's let it equal some value of 4 everywhere but at x equals 1, that horizontal asymptote. But we might define this function to be at 1. Let's see, we're going to have 1 when x is 1. So in other words, at 1, 1, I have a closed circle. And then for the rest of the time, we have this here with this open circle at y equals 4. So again, that's going to be false. Not many things we can assume here. Number 18, if f at 1 is positive and f at 3 is negative, then there exists a number c. Oh, this is very tempting, but is our function, let's see, what was our function? Let's just call it f of x. Is f of x continuous? We were not told it was, so this is going to have to be false. Very tricky. All right, let's look at number 19. And with number 19, let's see, f is continuous at 5, and f at 5 is 2. So we have a lot going for us right now. We're continuous and we have the 0.52. And we're told that here for 3. So then this limit of f of blah, blah, blah equals 2. Let's plug in and see. So we're going to have here, once we plug in, we're going to have 2 squared, which is 4. And 4 times 4 is 16. 16 minus 11 is 5. So now we have f of 5. and the limit as x approaches 2 of f of 5. Well, here it has to be 2 because we were told that f was continuous. So that one, as weird as it looks, has to be true. For number 20, it sure would be nice if this was true, but again, it is not. This one is false. Here, if we sub in, notice we get 0 over 0, and we have no idea what 0 over 0 is. We can't say that it's 1. If we did just say, because I know somebody's going, why? If we said it was 1, then we could disprove this by multiplication. Then 0 here times 1 is 0. And y'all are like, well, yeah. But what if I said 0 over 0 was 17? Well, by the same rationale, that would mean then 0 times 17 is 0. Well, yeah, that's true. But which one is it equal to? Is it equal to 1 or 17? They're definitely not the same amount. So that's why we say we don't know what it is. This one does not exist. It's going to be false. There's no really factoring or anything you can do. This one is one that you would just have to look at the limit as x approaches 0 from the left of our function. And if we look at this from the left, keep in mind you're going to have something that's always positive. Well, to the left of 0 is negative. So here you're going to have something negative. And if we look at the limit as x approaches 0 from the right, well, then you're going to have something positive over something always positive. Notice the limit from the left does not equal the limit from the right. So this actual limit does not exist. Number 21, the limit as x approaches c of f of x equals 11, then f is, or equals L, then f at c equals L. Well, that's doing an awful lot of assuming here, because the limit can have one value, but the actual function's value could be something else, because this is the intended y value. This is the actual y value. That's not always the same, so this one is false. And then number 22. So f is undefined at x equals c. Okay. And f of x approaches c does not exist. Well, let's draw it out and see. We are undefined at x equals c. So somewhere over here, let's say on the x value, we have this c, and we're undefined there. Then the limit, well, no, not necessarily. I don't think this means a vertical asymptote. I think she's talking about here, this just being an open circle. And we definitely could draw something very quickly on each side and see that the limit as x approaches c does exist. It's just not going to be defined there or continuous there. So number 22 is false. All right, number 23, we are skipping. I'm not interested in seeing several variations. Well, actually 60 some odd variations of drawings on that, or 2 drawings that everybody else copied. So let's move on to 24. So here we're going to look at the limit as x approaches 2 from the right of f of x. And then I'm going to add to it 5 times the limit as x approaches 2 from the right side of g of x. So hopefully this is a matter of plugging in here. So the limit as x approaches 2, so we've got positive 2 here, and we're approaching from the right side, so we're approaching in from this side. Even though that's an open circle, the intended y value from that direction is 1. So over here, I know the first part of this is going to be 1 plus 5 times, and now we need to find the limit as x approaches 2 from the right of g of x. And if I sum in 2 there, I'm going to have 4. 4 plus 4 is 8. So I'm going to have 5 times the square root of 8. And the square root of 8 will break down. But we can break it down. Sometimes you'll see this, and sometimes you won't. 8 is 2 square root of 2. So that's going to be 1 plus 10 on the square root of 2. Alright, so let's look at B. So I need to find the product of these two limits. So the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. And let's see, the limit as x approaches 1 of f of x, again tracing in from both the left and the right sides, we're going to be here. So that's a nice value of negative 2. So we're going to have negative 2 from this side times, and if we sub in 1 up here, we're going to get the square root of 5. And so our answer is negative 2 square root of 5. Alright, our next problem, again, dividing up these limits as x approaches 2 from the left of f of x. We're going to see what that value is over the limit as x approaches 2 from the left of g of x. Well, the limit as x approaches 2 from the left, limit as x approaches 2 from the left looks like it's going to be coming in this direction. So I have negative 1. So here I'm going to have negative 1 over 2 from the left. I think that was going to give me the same value as we had earlier. It's going to be the square root of 8. And we're perfectly okay to leave it like this. You might rationalize it, but it's really not necessary. I'm going to go ahead and rationalize it because I think some people would want to see that rationalized. Multiply top and bottom by the square root of 2. So I'm going to have negative square root of 2 over 2 times 2. So negative square root of 2 over 4. But again, I had much rather you leave your answers as negative 1 over the square root of 8. Alright, with letter D, we're going to be squaring our function. So we're really looking at the limit as x approaches 4. And to write in that function g, again, notice it's the square root of 4 plus x squared. And following this notation, that's all going to be squared. So here, let's go ahead and sub in. So this squared, actually before we sub in, we can actually move out that square and look at this as the limit as x approaches 4. I think this will be easier. The square root of 4 plus x squared, I could write, that would be great. All squared. We're more than welcome to move that squared out and find our limit, then square our answer. I think that'll work out better for us. And so that's going to be, we plug in our 4 here. So we're going to look at the square root of 20, because that's going to be 4 squared plus 4. And then we're going to square that, so that's just going to give us 20. For number 25, we have to find the values of k and m so that the function is continuous for all reals. Now we do have 3 particular steps that we would go through. I'm just going to write out these, but then we're really just going to jump to the algebra part of it. The first thing we would have to show is, does f at c exist? That was our first thing. Our second part, we had to examine the limit as x approaches c from the left of the function. Does that equal the limit as x approaches c from the right of the function? And lastly, the third major part of this, did the limit as x approaches c of the function equal f at c? That's going to prove continuity at a point. Now, if we're trying to find the variables k and m, so that the function is continuous, well, then we're going to assume a couple of these things already happened, and we're just going to set up our equations that we need in order to solve for our variables. And so the first equation that we need, I'm going to change colors here. We're going to sub in -2 over here. And so I'm going to have +4 plus 2k plus 3 equals, and then I'm going to plug in -2 down here. So I have -4 minus 3. And so when we solve this, I have 7 plus 2k equals -7. So I have 2 times k equals -14. And so k is going to be -7. So there's the first part of this. Got through that one pretty quickly. And I'm going to change colors, and we're going to apply the same techniques over on the other side. And again, this is all really coming from the fact that our limit from the left has to equal the limit from the right. So all of this is from this fact up here. And that's always going to work out that way. Okay, so again, setting up the same steps that we did earlier. However, this time we're subbing in 3. And whenever we sub in 3, we're going to have 2 times 3 minus 3. That has to be equal to, because we're forcing this to be continuous, 4 minus 2m. So I have 3 equals 4 minus 2m. And so let's see, subtracting 4. So m is 1/2. All right, so we found our variables. And again, last time here, just making sure we understand this whole setup right here is coming from the fact of that limit has to exist. All right, so for number 26a, we're going to go through all of these. Now, you have the absolute value of x, so the limit as x approaches 0 of f of x, that's just going to be equal to the absolute value of 0, which is 0. And the same is true over here on this other part. The absolute value of negative infinity is going to be positive infinity. All right, so looking at part B, and this problem came up earlier as well, you're going to end up with 0 over 0, and then we're going to have to break that limit apart and look at it from the left and from the right. And when we do that, from the left is 0 is negative, and from the right is positive. So this one is going to be those rare ones where 0 over 0 does not exist, but that's not always true, and I'm going to write that on here. That's not in always. 0 over 0 usually means we've got to go back and factor and cancel. We've got to look at our limit from the left and the right, and again, it's not going to exist. All right, so for part B, whenever I plug in -5, that's going to generate for me a positive 1. Now, if we plug in, let's see, infinity, we're going to have, let's see, infinity over that other infinity. Gosh, it looks like that one's going to end up here tending toward infinity there. So over the top and infinity over the bottom. So this is going to end up being a 1. And again, we have to be careful here. This would be better if we did a t-chart and we go through and plug in various values and see how they are increasing. Or if we remembered the graph of this, we have an open circle here, and then we're positive on this side and we're negative below here at 1 and 1. That'll also help. Okay, for our next one, notice here we have constant values, so our answer is automatically that constant value. Alright, so for the next one, we have our function cosine, and if you don't know your trig functions, you need to know those values, or ask me for something to help you with the little hand trick to help you remember those, either one. Alright, so here we're going to find cosine of 0, which is going to be not 0, but positive 1. Now over here, as x approaches infinity, if we think about the graph of cosine, the graph of cosine always did something like this. And notice that cosine never went below -1 and it never went above +1. So this limit as x approaches infinity is bouncing between -1 and +1, and it's not settling on a for sure value. So here it does not exist. Okay, for our next one, looking at 1 over x, again, it does help to remember that the graph of 1 over x does something like this. That will help you, but you don't have to know that. Over here, our limit as x approaches 0, that's not a one-sided. It's just going to be 1 over 0, which does not exist. And we can see that from the graph as well. Right, now over here we have to be careful with this. We are going to have 1 over infinity, which is 1 over a very big number, which is going to tend towards 0. And the same thing is true over here, 1 over negative infinity, that's still going to tend toward 0. Right, and then for f, we do need to go ahead and just sub in our values. And so if we sub in 1, I'm going to have 5 over -1, so that's going to give me -5. And if we plug in 2, notice we're going to get 6 over 0. That's a vertical asymptote. 2 is just one-sided limit here, so this one does not exist. Okay, and then over with our infinities, notice here that's going to end up being a power struggle because we're looking at x plus 4 over x minus 2. And notice here, there's our highest powers, and so this is balanced. So it's the ratio of those coefficients, and it's going to be 1. And the same is true going to be down here. Even though we're approaching negative infinity, that's still balanced, and so we will be approaching positive 1. Alright, now for part G, we are subbing in 0. And if we plug in 0, it looks like we're going to have -2 over -4, which is a nice day of 1/2. If we sub in -2, we get -4 in the numerator over 0. This is not one-sided, so does not exist. That's nice. And then if we plug in +2, I think we're going to run into an issue because we get 0 over 0. Again, that means we need algebra magic. Do not write, does not exist there. You don't know that. So we need to factor, and that denominator is the difference of two squares. So we're going to have x minus 2 times x plus 2. We have a removable discontinuity there, so we're going to remove that. Remember, that's a 1 left on top. And now if we redo our limit, we have 1 over 4. All right, now for the infinities. And again, this is going to be a power struggle here. Notice if we just grab the highest exponent x we see on top and the highest power we see on bottom, notice that this is going to be bottom heavy, so that's going to tend toward 0. And it looks like we're going to have the same power struggle down here as well. Even though we're heading toward negative infinity, that bottom is squared. So let's see, bottom heavy, yeah, we're still going to hit 0 there. All right, and for part H, and almost, it's the reciprocal. So let's plug in 2, and we're going to have 0 over 0 again. So that means we're going to have to do some factoring and canceling. Don't say does not exist. You don't know that. So we have x minus 2 times x plus 2 over x minus 2. Those are going to cancel. Reevaluate your limit, and you should get 4. If we plug in 0, then we're going to have -4 over -2, which is positive 2. And now we address our infinities. We're tending toward positive infinity. Notice here that we have x squared over x. So that's just going to grow without bounds, so that's positive infinity. Now this is where we have to be careful with our signs. With negative infinity, We are still going to tend toward an infinity, but notice the top is positive, but the bottom's going to be negative. So this one's going to tend toward negative infinity.